We have got it. So today is a little bit different. Normally we are inviting hardcore researchers on various aspects of chemistry, but today it's a very special, very interesting thing. We have today with us Scerri, who is a chemist, a writer, and philosopher of science, and this makes this talk very, very interesting. Currently, he's a lecturer at the University of California in Los Angeles. He wrote multiple plethora books. He's founder and editor-in-chief of the Foundations of Chemistry, an international peer-reviewed journal, which covers the history and philosophy of chemistry. He's a world authority. As I was searching his name, he's an influential, I think the second or the first influential chemist on the whole world, and he's a world authority on periodic table. So today, he will give a talk about the brief history of a periodic table, and we are really eager to hear from him. And we would like to thank him because currently it's 12 o'clock at Los Angeles, and this is a midnight talk for him. Very difficult. Thank you very much, Eric.
Thank you. Thank you for your kind introduction. And nice to see you. And let me make a start. So, yeah, a brief history of the periodic table. Now, it's a huge subject, and I only have about 50 minutes, so let me get started straight away. Let me try to find my my page turner. Here we go. All right. Now, of course, it's been said, many things have been said about the periodic table, but one of them is that it is the ultimate infographic. A graphic display which is used to convey information of all kinds. It's something of a scientific icon, one of the most powerful scientific icons that we have. It's been adopted by artists. This is Blair Bradshaw from the United Kingdom, who has this rather fanciful version and many versions. He's done about, I believe, 25 paintings around the theme of the periodic table. There's a periodic table of almost anything you can mention these days. Here's one of my favorites, a periodic table of football, or soccer, as we say in the United States. If we restrict ourselves even just to the real periodic tables of chemistry, there have literally been over 1,000 tables that have been devised in all shapes and sizes. You can see here these clock face type of representations, and then there are three-dimensional loops and helices and pyramidal tables and stack tables, and you name it. There are these immense periodic tables on the sides of buildings. This one is from the University of Murcia in Spain. There is, of course, the very famous one outside the institute that Mendeleev worked in St. Petersburg. Some of you may have seen this. I like to ask this question: how should chemists and chemical educators react to all the attention that the periodic table is getting? And the simple response is, I think we should embrace it, because chemistry still needs all the positive public relations that it can get. It's no secret that chemistry has generally a bad press because of all sorts of things like pollution and the notion that chemicals are somehow a bad thing. You know, people say, oh, are there chemicals in this food? Books on the periodic table are now beginning only to catch up with popular books on physics and biology. For a long time, you know, when you went into a bookstore, if you can still find a bookstore, you would find shelves and shelves on Einstein and on Newton and what have you, and on Darwin, on genetics, but almost nothing on chemistry, which is in a way slightly mysterious, given that the profession of chemistry employs many more people than physicists or biologists. I believe even more than physicists and biologists put together. It is, of course, the periodic table is the paradigm of chemistry in many senses of the word. It's literally a framework. It could be thought of as the paradigm of chemistry, even in the sense of Thomas Kuhn. it is, of course, the organizing principle of much of chemistry. There is a popular view in, for instance, in philosophy of science, that physics and biology have big ideas, such as quantum mechanics, relativity theory, Darwin's theory of evolution, whereas chemistry is perceived to lack big ideas. We chemists know that that's incorrect. There are at least two big ideas in chemistry, the periodic table and chemical bonding. And these two are intimately related, intimately connected. Now, thankfully, there's beginning to be a philosophy of chemistry, although chemistry was ignored by philosophers of science under the impression that there was a lack of profound ideas. There's now beginning to be, since the mid-1990s, these are the books that I've participated in the philosophy of chemistry. And as Dinos mentioned at the beginning, there's an international journal, Foundations of Chemistry, which is now in its 24th year. Now, a word to chemical educators. I don't know if there are any chemical educators in the audience. I personally am a chemical educator as well as being a historian and philosopher of chemistry. I think, and it's not a particularly original idea, that the periodic table could be made into a more unifying strand running through chemistry courses. Of course, it's mentioned in chemistry courses, and of course, one refers to it in order to look up atomic weights and to rationalize much of inorganic chemistry. But it's not really being used sufficiently well, in my opinion, in order to bring about greater unification. And in doing so, I would propose beginning with the periodic table as discovered according to the properties of elements and compounds. So my suggestion is to expose students to the properties of, let's say, some halogens, some elements in group 1, and to gradually move towards the periodic table. Now, the popular view in chemical education these days seems to be to first consider atomic structure and then to somehow arrive at the periodic table, to quickly move to the periodic table and to use atomic structure to explain the periodic table. And so chemistry is being taught as if it was physics. Chemistry is being taught as if it was quantum mechanics. Chemistry is being taught as if it was atomic structure. There are many books that now propose an atoms first approach. And this has certain advantages over the more traditional view. On the other hand, it is a very reductionist view. And again, it's putting atoms first, literally, and chemistry second. In a sense, what it's doing is it's putting the cart before the horse. It's putting the cart of atomic structure and quantum mechanics before the periodic table, rather than putting the horse, the periodic table first, and then using the periodic table as a means to introduce students to atomic structure and quantum mechanics. A colleague of mine at Purdue University many years ago used to say, you can ask a student of chemistry these days to give you the configuration, an electronic configuration of chlorine, and the chances are the student will be able to list the electronic configuration of chlorine. But now ask the student, what is chlorine like? And they haven't the slightest idea what chlorine is actually like. So this is putting the cart before the horse. Now, I'm going to talk about some open questions having to do with the periodic table. Of course, it's not a closed book. It is a still developing story. Quantum mechanics is generally believed to explain the periodic table. And of course, to a first approximation, it does provide a very, very excellent explanation of the periodic table. This is the justification for why it is put up front in chemical education. One question that is interesting to ask is, to what extent does quantum mechanics explain the periodic table? Does it explain everything? Of course, the answer is it doesn't explain everything about the periodic table. So it's a case of partial reduction, if you like. Now, I'm talking to an audience of chemists, so I hardly need to remind you of what periodicity actually is, but still, I'm going to pause for a moment and consider what is chemical periodicity. If we line the elements up in order, here I've done it in order of atomic number, chemical periodicity consists in the fact that as we walk along this line of the elements, every now and then there is an approximate repetition in the properties of the elements. So for example, you have lithium, you walk along the elements, you arrive at sodium, which is very similar to lithium. You walk further and you arrive at potassium, which is similar to the previous two elements. And so this element line gets converted into a two-dimensional table, such as this. Right? So this is the beginnings of a periodic table. You notice I stopped deliberately at manganese, which is number 25, and I don't put the next element in. The reason being that if you try and put the next element in, you run across a problem. Iron, Fe, is not a noble gas. Right? So what do we do? What did Mendeleev do? What did the discoverers of the periodic table do? Well, they did something quite clever. They, as it were, excluded iron, and they threw it out into group 8 of the periodic table. In fact, they did it for iron, for cobalt, and for nickel. And by doing that, periodicity is maintained because the very next element, copper, has a valence of 1. It may not be the most common valence, but it does have a valence of 1, so it justifies being in group 1. Zinc has a valence of 2, and so on. And then he does this again with ruthenium, rhodium, and palladium. And then he does it again with osmium, iridium, and platinum. And so we have the original periodic tables were 8-column periodic tables, which actually displays periodicity rather nicely, especially for beginners, because it's simple periodicity. Every 8 elements, you get a recurrence. But with this proviso of these elements that have been somewhat banished or excluded into this mysterious group 8. In the current periodic table, we don't do that. In the current periodic table, iron, cobalt, nickel have their own groups. Here they are. Iron, the iron group, the cobalt group, and the nickel group. And the current periodic table is not an 8-column table, it's an 18-column table. Okay. Now this creates the banishment of another bunch of elements. In fact, as many as 28 elements shown in yellow here, the so-called F block, is being excluded. And good students, when first shown the periodic table, will notice that there's something funny going on here because you have element 56, and then in the very next element appears to be 71, lutetium. Then you have radium, 88, and then suddenly 103. What's going on? Well, what's going on is that this yellow block really belongs in between 56 and 71 and 88 and 103. So why not do that? In the same way as the transition metals were brought in to the main body of the table, we can make that kind of move again, and we arrive at a 32-column table, where every element follows every other element in order of atomic number. So there's a sense in which this is a better periodic table. Aesthetically better, just neater, because there isn't that break, there isn't that exclusion of the F block elements. And some textbooks have now started publishing this 32-column table. Okay, so now let me begin my brief tour of the periodic table, brief historical tour. I'm going to start at a fairly arbitrary place, Dalton, who of course revived the ancient Greek notion of atomism, the difference being that he gave the atoms of different elements actual weights, or he set about estimating their weights. Here's one of his early tables. You see hydrogen is 1, you see nitrogen or azote 5, and so on. This is in 1808, one of the earliest sets of atomic weight. Following that, other people began looking at the atomic weights of elements and began noticing a couple of interesting things. Here are two, you could call them philosophical principles, which contributed to the eventual discovery of the periodic table. We are still pre-periodic table. And those two principles are triads of elements and Proud's hypothesis. Excuse me for jumping. So triads. Wolfgang Dobereiner in Germany noticed that there are groups of 3 elements in which one of the elements has the average atomic weight approximately, and also the average or intermediate chemical behavior. One of the prime examples is, of course, lithium, sodium, and potassium. Atomic weight 7 for lithium, atomic weight 39 for potassium. You add the two together, you divide by 2, and you get approximately 23. It's a remarkable result. He found other such triads, including the chlorine, bromine, iodine triad, the sulfur triad, the calcium triad. Now, of course, it's not exact. I compare, for instance, bromine has an atomic weight of 79.9, but the average of taking chlorine plus iodine and dividing by 2 is not quite 79.9, it's 81.19. Right? So it's approximate, but it's highly suggestive because it happens again and again with different groups. However, because of the approximate nature, and because some people began to think this was just mere numerology, the idea went into decline. However, as an interesting twist, if we now consider modern triads based not on atomic weight, but on atomic number, which, as you know, is the more correct ordering principle for the elements, you find that atomic number triads become exact, not approximate. Consider the chlorine triad. 17 plus 53 is 70, divided by 2, you get exactly 35. Similarly with the other triads. It becomes exact. And of course, we know why it becomes exact, because we're now dealing with protons, which come in whole numbers. So triads appear to have made a comeback, right? They were suggestive, they were of interest to people. They were then underwent a period of decline, and now it would appear they've made a comeback. Now, I'm alluding to the notion of theoretical comeback, which is due to the philosopher of science, Imre Lakatos, the Hungarian philosopher of science. Here is a picture of Imre Lakatos. Here is a periodic table, a 32-column periodic table, in which I have superimposed triads of elements. You can see they're all over the place. And there's nothing particularly mysterious about them. We know why triads are what they are. For instance, consider the chlorine, bromine, iodine triad, which is this strip here. Why does this happen? Well, because on going from chlorine to bromine, one goes through 18 elements. From going from bromine to iodine, you go another 18 elements. So it's hardly surprising that bromine is in the middle of those two intervals. Right? So we understand triads. There's nothing mysterious about them. Eventually, if these very heavy elements are discovered, there will even be triads in the F block. So almost every element, or many, many elements, are members of one triad or another, sometimes of two triads. The second, we might say, philosophical principle that led to the discovery eventually of the periodic table is Proud's hypothesis. Proud was a Scottish physician working in London. He noticed something fairly obvious. If you look at a set of atomic weights, it becomes clear that most of the elements are whole number multiples, or their weights are whole number multiples of the lightest one, hydrogen. There are exceptions, which I highlight in yellow here, which are not whole number multiples. But the fact that so many of them are is again suggestive. And the obvious suggestion is perhaps all the elements are literally composites of hydrogen. They're made up of hydrogen. That's Proud's hypothesis. Now, I bring in another philosopher of science, Karl Popper, who tells us it's not so much whether an idea is right or wrong that's important, it's only whether it's refutable, whether it can be shown to be incorrect. It turns out that Proud's hypothesis is refutable and was refuted. It was refuted by the accurate experiments that conducted by people like Berzelius and Stas, who showed that actually many elements are not whole number. In fact, the majority of the elements are not whole number multiples. In fact, strictly speaking, none of them are whole number multiples of hydrogen. And yet, this hypothesis has made a kind of a comeback in the Lakatoshian sense. How? Well, in the sense of protons, right? In the sense of protons, we could say that all atoms are composites of hydrogen. So we're going to ignore neutrons for the sake of this suggestion. And also, astrophysically, we're told by astrophysicists that the elements were literally formed from hydrogen and helium, or two hydrogens fused together to give helium, and in principle, two heliums fused together to give beryllium. Of course, it's more complicated than that, but it is a sense in which perhaps Prout's hypothesis has made a comeback. They've both staged an interesting return or comeback. Interestingly, Mendeleev claimed that he disliked both of these ideas. He claimed he didn't like Prout's hypothesis because to him this smacked of mysticism. He didn't like the idea of the unity of all matter. He also claimed that triads were misleading and that they had misled pioneers into a kind of numerology. And indeed, they had led many people to a kind of numerology. But funnily enough, Mendeleev himself used triads. Not only did he use triads, but he used triads with a vengeance, because he used triads vertically and horizontally. He published this little table. If you want to discover the atomic weight of an unknown element, now selenium was known, you could do it by summing the atomic weights of the four surrounding elements, here, sulfur, bromine, tellurium, and astatine, arsenic, not astatine, and dividing by 4. In this case, it comes to 79, and the then known weight of selenium was 78. So he was showing that this was a good way to determine the atomic weight of unknown elements by using it on an element that was known. So he may have said he disliked triads, and of course he disliked certain aspects of triads, but he actually used triads. It has to be said that Mendeleev also rejected the following atomic theory. He didn't believe in atoms. He didn't even believe in the expression atomic weight. He preferred the expression elemental weight. Valency theory, when it was first introduced, Mendeleev would have nothing to do with it. When the electron was first discovered, he distanced himself from such notions. Theo might have some things to say about that, having edited various books on the discovery of the electron, etc. When radioactivity was first discovered, he actually visited the Curies to try and see for himself whether this was real, and he came away muttering, I still don't believe it. When noble gases were first discovered, he didn't take them serious, and so on. And famously, electrolytic dissociation, he rejected. It's apparently the reason why he didn't get the Nobel Prize, because he quarreled with Arrhenius and so on. So altogether, very scientifically conservative, and he had one single-minded idea, the periodic table, which he defended against all comers. A crucial step in the development of the periodic table was the important conference in Karlsruhe, in which such things as atom and molecule and atomic weights were rationalized. The Italian physicist and chemist Cannizzaro produced the set of atomic weights that was adopted widely. And once that set of consistent and agreed upon atomic weights was available, it really was a case of multiple discovery among many people. In fact, there are said to be 6 discoverers of the periodic table, of which Mendeleev is the last of the 6. He may have been the most successful, and he may have been the one who propagated the idea most strongly, but he was the 6th. 7 years before Mendeleev's famous table of 1869, we have the Frenchman, Alexandre-Émile Bégayer de Chamcourtois, publishing this rather interesting helical system in which the elements are arranged in a line. The line is wrapped around the cylinder. And as you move down vertically on the cylinder, you can begin to see the familiar grouping of lithium, sodium, potassium. And then this is a bit off the line, but beryllium, magnesium, and calcium, and so on. Right? A rudimentary, fairly successful periodic system. Newlands in London had many successful, relatively successful periodic tables in which he even reversed the elements tellurium and iodine. He placed tellurium before iodine, even though the atomic weights are such that tellurium has a higher atomic weight than iodine, the famous pair reversal. It's there in Newlands. Heinrichs, a Danish polymath who had emigrated to the United States as a young man, published this rather elegant bicycle wheel periodic table in which all the groups are already there. This is about 5 years before Mendeleev. If you look, if you can see it, it's rather small, but oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, antimony, bismuth. It's all there. And the noble gases, not the noble gases, the halogens, fluorine, chlorine, bromine, iodine, and so on. William Odling, also in London, had a number of successful periodic tables. He too reversed tellurium and iodine. You'll notice an increase in atomic weight, and all of a sudden you have tellurium being placed before iodine, even though it has a higher atomic weight than iodine. Why? Because the chemistry fits better if you make the reversal. There was no justification, no true justification. But one could say this is a bit of an ad hoc move, right, to make the chemistry work, but with no profound independent justification. Of course, that was yet to come. And the fifth discoverer is Lothar, Julius Lothar in Germany. He too has reversed tellurium and iodine. He places tellurium before iodine, even though it has the higher atomic weight of about 128 as opposed to 126. So Mendeleev is not the first to have done that. At least 3 people had done that before him. And now we come to the sixth and final discoverer, Dmitry Mendeleev. And of course, as the popular story goes, and in a sense, rightly so, the thing that distinguishes Mendeleev is the fact that he made predictions and that the predictions came out correctly. He famously predicted 3 elements that I show with asterisk symbols here. These elements were eventually called scandium, gallium, and germanium. He predicted 1 more initially. This element with an atomic weight of about 100 was synthesized in the 1940s and has become known as technetium, but it was predicted even then by Mendeleev. I have a book in which I discuss multiple discovery and simultaneous discovery called The Tale of 7 Scientists. These are not the discoverers of the periodic table. I discussed 7 other scientists, including chemists and physicists. And I talk about the importance of minor contributors. This is something of a critique of Thomas Kuhn's view that there are scientific revolutions. I'm wanting to claim that really, if you look closely enough, of course, Kuhn did look closely. He was a fabulous historian. But as I see it, there is continuity, not discontinuity. One can always find precursors. One can always find intermediate little steps that led up to the major discoveries. Now, a little word about prediction. Since Mendeleev is fated because of his, feasted because of his famous predictions, there is a long-standing debate among historians and philosophers of science concerning the relative value of prediction and what's sometimes called retrodiction or accommodation. In other words, explanation of data that's already known. Traditionally, one thinks of prediction as being more dramatic. And of course, psychologically, it is more dramatic. If the scientist predicts something which is eventually found, it's as if the scientist knows the secrets of nature in advance. And if the scientist accommodates something that's already known, it simply doesn't appear that dramatic. However, there is a long-standing debate on this. What counts more to the scientists, to the experts. A well-known example of this has to do with general theory of relativity. If we consider Einstein's general theory, it had initially two tests. One test involves the genuine prediction by Einstein that a beam of light passing next to a massive object will be slightly deflected. Einstein predicted the deflection of a beam of light passing the sun would be 1.75 seconds of arc. A few years later, Eddington famously went during a total solar eclipse and observed a deflection of 1.98 approximately, and Einstein became famous overnight for this dramatic prediction. Einstein's theory also makes an accommodation or a retrodiction, right? Meaning a prediction of something that's already known, retrodiction. And this is the equally well-known excess precession of the perihelion of Mercury. This was something that Newton's theory could not account for. Newton's theory does account for the bulk of the precession of the perihelion, but not quite. The gap is 43 seconds of arc per century. Right? In a way, it's minuscule, but it was recorded over a period of many, many years, and it was known to be a problem with Newton's theory. When Einstein predicts, I put in inverted commas because he's not really predicting this, it's been measured, Einstein retrodicts a precession of 42.9 seconds of arc, right? A wonderful retrodiction. The historians who have looked into this, by which I mean mostly Stephen Brush, have found that this retrodiction was taken more seriously by the scientists at the time than the dramatic prediction. So it's not the case that prediction always carries the prizes. In the general population, perhaps prediction is more worthy of awards and so on, but it's by no means a foregone conclusion that prediction wins the prizes. In which case, let's go back to Mendeleev's three predictions. Yes, he made three dramatic predictions, and yes, they turned out to be 100% successful. But let's look at the other predictions that Mendeleev made. He made a total of, 16 predictions. Half of them were wrong. Now that's 50-50, right? That's not that good. I mean, astrologers can get it right 50% of the time. And here's Mendeleev making predictions, and it only comes out 50%. So if we really were to put a lot of credit on his predictions, shouldn't we look at all his predictions and declare that actually he's not all that dramatic? Okay. Moving back to my historical timeline, in 1894, there was a discovery made that began to spell trouble for the periodic table. Ramsay and Rayleigh in London discovered argon, this mysterious new element that just wouldn't fit for many reasons. Here are some of the reasons. It had an atomic weight of 40, which meant it didn't seem to have a place in the periodic table. For one reason, there already is an element of atomic weight 40, calcium. So what are you going to do with this new element that also has an atomic weight of 40? There was a big debate as to whether argon was monoatomic or diatomic. Of course, it turned out to be monoatomic. All the noble gases are monoatomic. And worst of all, it was completely unreactive, which made some people say it didn't even belong in the periodic table. Mendeleev began by, first of all, rejecting it, and then he had this wonderful idea that maybe it was triatomic nitrogen. Nitrogen has a weight of 14, and if you multiply it by 3, you kind of get whatever it is, 42 or something. Right? So it's there, it's in the right ballpark. Then things got worse for the periodic table because Ramsay and Rayleigh discovered helium, neon, krypton, xenon. Right? Now there's serious trouble. You've got 5 elements that nobody seems to have discovered and that can't be fitted into the periodic table. Is this the end for the periodic table? Certainly troublesome. For about 5 years, there was complete mystery. And of course, Ramsay solved the problem himself. He created a new group. Here is a cartoon from Punch magazine of the time. He's proudly pointing to his new group 8. When Mendeleev heard about this, he was delighted. he claimed that, well, this shows the strength of the periodic table because it could accommodate this new group successfully. Now, it is widely believed that nobody had predicted the noble gases. Certainly, Mendeleev didn't, Ramsay, nobody predicted it of the well-known chemists, but a slightly lesser known chemist, the Danish chemist Julius Thomson, did predict the noble gases. He predicted some new elements which would have atomic weights. Here they are in red: 4, 20, 36, 84, and so on. And below it, I show the atomic weights of the noble gases all the way up to oganesson. And if you calculate the error, the average error is only 1.6%. I find this remarkable. And it's just not a well-known fact, not well enough known fact that somebody did predict them and predicted them incredibly well. Now, of course, it's not all that complicated. You look at gaps in atomic weights, and where there's a big gap, you speculate that there might be an element. Or in this case, 7 elements. Back to my historical timeline. I like to say physics begins to invade chemistry at the start of the 20th century, at the turning of the 20th century. Why? Because of some very dramatic discoveries. Röntgen discovers X-rays. Becquerel the next year discovers radioactivity. And the very next year, Thomson discovers the electron. These 3 discoveries were, of course, to have a profound influence on the whole of physics, on chemistry, and on the periodic table, on trying to understand the periodic table. A few years later, Rutherford probes the structure of the atom, alpha rays, beta rays, gamma rays, and so on. The Curies conduct further experiments on radioactivity. Moseley discovers the important concept of atomic number, which means that we have a better ordering principle for the elements than atomic weight. This is taken from a recent book, by the way, on Moseley for Science, King and Country. This is the famous graph of atomic number along the y-axis and the square root of frequency of X-rays, which showed a linear dependence. With that discovery, we now had a fundamental non-ad hoc justification for these pair reversals. Why does tellurium come before iodine? Because the atomic number of tellurium is 1 lower than that of iodine. You don't have to argue in terms of chemical properties anymore. It's because atomic number orders them in that way. There are a total of 4 of these. There's the argon-potassium anomaly, or pair reversal. There's the cobalt-nickel, and there's one thorium and protactinium. When Moseley made that discovery, it became possible, or it was realized, that there were precisely 7 elements missing between the boundaries of the old periodic table, by which I mean hydrogen to uranium, 1 and 92. Before Moseley's discovery, it was never clear just how many elements remained to be discovered, because the gaps between successive elements in the periodic table are notoriously irregular. Sometimes it's 1 unit, sometimes 2, 3, 4, 5, all the way up to 6 and even 7, I think, on one case. And even reversals. With atomic number, it becomes categorical. It became clear which atomic numbers were missing, and it became a race for who would find, and these are the elements shown in color here: technetium, rhenium, hafnium, astatine, protactinium, and promethium, and francium. Mustn't forget francium in green here. I have a book on this subject, on the discovery of these 7 elements, which the late Oliver Sacks very kindly wrote a preface for. Continuing on my very quick historical tour, the old quantum theory of Planck, Einstein, and Bohr gave us, especially in the hands of Bohr, gave us the idea of electrons orbiting in shells. And this provided perhaps the first explanation of the periodic table. Why are the elements in groups the way they are? Well, if you look at the configuration of lithium, you see 2, 1. This is a very elementary configuration based on just 1 quantum number. This is actually the Bohr Sommerfeld model, which involves two quantum numbers. I shouldn't perhaps use that diagram. The table, however, is one quantum number. Main shell, 2,1. In the case of sodium, 8,2,1. In the case of potassium, 8,8,2,1. What they have in common is they have an analogous outer shell. And this remains as the simple explanation for the periodic table, right? Analogous outer shell electron structure. This is 1913. Of course, quantum mechanics really became consolidated, it became rigorous, it became axiomatic between the years 24 and 26. I show many of the contributors here: Pauli, Heisenberg, Schrödinger, Dirac, Fermi, and so on, de Broglie. Now it became possible to get a better explanation of the periodic table. By solving the Schrödinger equation, one characterizes the different solutions by the use of three quantum numbers. If we add the fourth quantum number due to Pauli, now we can explain rigorously from first principles why the first shell can contain 2 electrons only, the next shell 8, the next shell 18, the next shell 32. So in a sense, here is an explanation for the periodic table, deductively obtained from the Schrödinger equation for just the hydrogen atom. And it gives us the whole periodic table. Right, dramatic, impressive. I mean, this is the reduction of chemistry in a sense. And physicists became very bold and made statements such as, now physics is capable of eating chemistry with a spoon, on which Kostas Stavroglou has written an entire book, or a biography, I believe you have, of Fritz London. Now, is that a complete explanation? Well, if the shells filled sequentially one after the other, it would be a wonderful explanation of the periodic table, but they don't fill sequentially, because if they did, then you would have helium number 2, neon number 10. Well, that's true. But then the next shell, if you added 18 to that 10, you would get 28. Nickel is not a noble gas, nor is neodymium, and nor is darmstadtium. Right? So the closing of the shells occurs at these numbers, but the closing of the periods occurs at these numbers. These are the noble gases. In other words, the shells are not filling sequentially. I mean, this is no mystery. We understand why this is the case. The two sets of values I'm showing here don't coincide because the shells don't fill one after the other. Although they begin to do that, you know, the first shell fills, then the second shell. The way they fill is rather diagonally, as summarized in the so-called Madelung rule, the n plus L rule, the sum of the n and L quantum numbers. So 1s fills first, then 2s, then 2p, then 3s. Everyone who's learned any chemistry is familiar with this, although it has a different name in every country. What is it called in Greece, as a matter of interest?
I think we have pretty much the same name.
Is it? Because in France...
In my high school course, we're saying the same.
Okay. Now, in 1969, during the celebrations for the 100th anniversary of the discovery of the periodic table, the Swedish theoretical chemist Lövdin set the community a challenge to try and explain this very simple rule from first principles. It is, he said, it is perhaps remarkable that in quantum theory, the simple Madelung rule has not yet been derived from first principles. And indeed, it still hasn't been derived from first principles, 53 years later. Many people have tried to do this. There are many claims in the literature to have solved this problem, but it's also recognized that it really hasn't been derived. I make a little digression. There is a long-standing controversy, especially in chemical education, concerning the filling of the 4s and 3d orbitals. 99% of textbooks, I haven't done a survey, I'm just estimating it, right? The vast majority of textbooks claim that the 4s orbitals are preferentially occupied and also preferentially ionized in the first transition series of elements. right? So 4s preferentially occupied and also preferentially ionized. Now that makes no sense logically, because students are being asked to believe that when it comes to the filling of orbitals or the occupation of orbitals, then 4s fills before 3d. But when it comes to emptying or ionizing, suddenly it's the other way around, because the 4s are known experimentally to be preferentially ionized, right? So what's going on here? To look in a bit more detail, we look at the curves involving the orbital energies of 4s and 3d. And of course, there's variation. When you reach, this is atomic number along the x-axis. When you reach numbers 19 and 20, potassium and calcium, then sure enough, the 4s orbital energy dips below 3d. And so it is logical that in potassium and calcium, 4s should indeed fill preferentially. However, when we go beyond calcium into scandium and the following transition elements, you'll notice that 3d has dipped below 4s. So 3d should be filling first, not 4s. And yet the majority of books tell you that 4s is filling first. Right. The real situation is that indeed 3d does occupy preferentially. And if it does preferentially occupy, then it's perfectly natural that 4s should follow, right? That should be occupied next. And therefore, 4s should also be preferentially ionized. There's no conundrum, there's no mystery. But it relies on accepting this fact that 3d is preferentially occupied. So the reason why there's a confusion in this is because it's not just a matter of adding an extra electron to the ones one had previously. You see, calcium is argon core 4s2. So the popular belief is, well, scandium is the next element, just throw in one more electron. 4s is already filled, therefore it must go into 3d. No, this is what scandium does. Scandium says, argon, 3d1 4s2. What's the evidence? Well, the evidence comes from, for example, the famous Charlotte Moore tables of atomic energy levels. These are available online these days from some agency in the US. I can't remember which one right now. If you look at the spectra of scandium 3+, scandium 2+, scandium 1+, and neutral scandium, right? And you look at the configurations, you can see very clearly that scandium 3+ is empty 3d and empty 4s, and the scandium 2+ ion is 3d1 4s0, right? So clearly 3d fills preferentially. Then the next electron goes into 4s, so it's 4s1, and then the scandium neutral atom is 4s2, right? So they've gone in one by one, but the first one to have gone in is 3d1, is a 3d electron. So this picture on the right is correct. The picture on the left is incorrect. And this picture meets both requirements. Now, you might ask, well, why not 3d3, right? If I'm claiming that 3d orbital level is low. Well, the answer is a fairly simple one. The 3d orbital is more compact. And the more electrons go into 3d, the more electron-electron repulsion there is. The 4s orbital is more diffuse, is bigger. So by going into 4s, the electrons are minimizing electron-electron repulsion. How many can you put in there? 2, no more than 2. Right? So electron-electron repulsion is minimized if 1 or 2 electrons, it's usually 2, enter that orbital. Here's a more technical version for the computational chemists, if any, in the audience. Right? You have the 3 configurations being compared, and here's the one that actually occurs. The 2 that do not occur are because of the DD repulsion term. This one has 3 such terms, right? The one that has the D3 configuration. So this one lacks that destabilizing DD repulsion. Okay, so contrary to what is stated in 99% of textbooks, the famous N+L rule actually only applies to elements 1 to 20 for the order of occupation, right? Because as soon as we get to scandium, 4s does not fill before 3d. So whoops, the Madelung rule appears to be in trouble. Some authors have suggested abandoning the Madelung rule. I am of the opinion that we shouldn't abandon it, but we should just state its limitations. And if we're not concerned with the precise order of filling, if we just want the overall configuration, then the Madelung rule still rules, if you like, except for the well-known fact that there are 20 exceptions to it in the strict sense, right? Because chromium and copper are S1 configurations, not S2 configurations. That's not dictated by the Madelung rule. And then there are 6 such elements in the second row, and 2 in the and some in the F block, a total of 20. Right, so we don't need to discard the Madelung rule, but we should be aware of its limitations. When it comes to predicting the periodic table as a whole, however, or when it comes to explaining the periodic table as a whole, the fact remains that 4s does fill before 3d, right? Because in calcium and potassium, or I should say potassium and calcium in order, that is indeed the case. 4s has filled first. So the best way to say this is that the Madelung rule still rules for the differentiating electron between any 2 successive atoms. I'm happy to go into this in question time if anyone's interested. I think I've labored the point a little too much. Let me go back to the main story. The Lovedean challenge of trying to explain this rule still stands. So the periodic table is not fully explained yet by quantum mechanics. That's not to say it can't be, but it has not yet been. Let me briefly turn. How am I doing with time? I'm already in 56 minutes. Should I stop there? Should I go on for a little bit? What's the feeling?
I think if we can go a little bit, so we can have time for questions, it would be nice.
All right. Briefly, relativistic quantum mechanics is becoming more and more of a big deal now in chemistry, because in a sense, relativity theory poses the ultimate challenge to the periodic table. And the question becomes, first of all, it's been used for some years now to explain such apparently mundane things as the color of gold. This turns out to be a relativistic effect. The fact that mercury is a liquid is a relativistic effect. But now, when elements 104 and 105 were discovered, Rutherfordium and dubnium, they did not behave in the way that they're supposed to behave, according to the periodic table. Right? So Rutherfordium is supposed to be, if you look above, like hafnium and zirconium. But Rutherfordium behaves more like plutonium, which is way over here. Similarly, dubnium doesn't behave like tantalum and niobium, but it behaves more like protactinium. Right? So trouble with high atomic number elements. However, when you move on to, for instance, copernicium, which is even heavier, number 112, and if you plot, for example, the sublimation enthalpies for these elements in group 12 of the periodic table, you get an almost perfect straight line. Copernicium does behave as it should behave. So it's as if the jury is still out. Relativity theory seems to influence some elements, but not others. The same thing is true of element 107, borium. It behaves like it should. I published a thing in Scientific American on this, and the editors got very carried away, and they showed the periodic table which completely disintegrating, which is taking it a little far, but you don't argue with the editors of Scientific American when it comes to selling their journal. They like to have dramatic pictures. Is there such a thing as an optimal periodic table? Let me just spend a moment on that and maybe stop after that. I believe there is, right? Although there are thousands of representations, and the periodic table I believe to be the optimal table is the so-called left step periodic table, due to a Frenchman, Charles Janet, in the 1930s. It's become much more discussed these days. let's take the standard 32 column table and make two moves, two changes. First of all, you move helium from there all the way to there, to the top of group 2. Why? Because it's got 2 electrons in it. Secondly, you take a pair of scissors and you snip there, and you take the entire S block and you move it to the right-hand edge, and you arrive at this left step periodic table. Okay. Consider the traditional table below. There's a very glaring anomaly in the traditional periodic table. Whereas all periods repeat in length, 8, 8, 18, 18, 32, the very first period, for some weird reason, doesn't repeat. Now, I mean, nature can be stubborn, can have anomalies, but this periodic table shows perfect regularity in that every period length is repeated. 2, 2, 8, 8, 18, 18, 32, 32. So on the grounds of elegance and regularity, this would appear to be a more fundamental periodic table. Now, some chemists don't like it because helium is traditionally believed to be a noble gas, right? Here, we're putting it among some rather reactive metals. Now, it turns out that helium does form some compounds. A few years ago, let's see, 2017, this compound was formed, admittedly at very high pressure, but there is a compound, at least one compound of helium. Okay, I think I better wind up now. I was going to say more, but I will stop now. I was going to say something about the debate on group 3, but maybe we can leave that open if anyone has questions. So thank you for your patience.
Thanks, Professor Scerri. Thanks a lot. So please, any questions, remarks? Professor Arabadzis?
Yes, thank you so much, Eric, for this really informative and nice talk. I have a question about the Madelung rule.
Yeah.
Is there, I mean, do chemists or physicists understand why the rule has not been derived? Is there a story for that? What's the problem? Is it computational complexity? Is it, what is the problem exactly?
Well, it's just a failure to derive it from theory. Now, I should say there are attempts, there have been attempts for many years using groove theory to derive this. And there has been some headway using a groove theoretical approach, which is, I mean, quite separate from quantum mechanics. I mean, it's just a mathematical approach. But in terms of physical theory, nothing doing so far. So we don't know what the problem is, in a sense.
Mm-hmm.
It feels like it should be something derivable. And it's something that is, you know, encompassing the entire periodic table.
Thank you.
There are a couple of Belgian authors who've published a very interesting book called Shattered Symmetry, in which they discuss this left step periodic table and they discuss the En-Passel rule, and they point towards possible solutions using group theory.
Professor Gavroglou?
Thank you, Professor Neochoritis. Eric, this was really an intriguing unfolding of what happened in the early years of this discovery. Tell me, what was Mendeleev's view to not the invasion of chemistry by physics, but the invasion of chemistry by mathematics? Because it was during that time that chemical thermodynamics and then all this, you know, different culture was in the making among chemists. So what was his view about that, since he was against atoms and against all the other constitutive things of, you know, the tradition that eventually dominated?
Yeah, that's an interesting question. I don't think he was against the introduction of mathematics. He didn't like numerology. And as I said, he didn't like people playing with these numbers and trying to find patterns. but I believe he does discuss in his book the idea of trying to find a mathematical formula that would explain the whole periodic table. So he wasn't averse to it. Not as hostile towards mathematics, no.
And what about chemical thermodynamics?
I simply don't know the answer to that. Would he? Let's see. He passed away in 1907. Of course, the early thermodynamics of Carnot and people like that would have been established, but the really serious thermodynamics, I guess, hadn't happened yet, and certainly the physical chemistry revolution had not taken place.
There was Van Hoff's work earlier on. But anyway, it's
interesting question. I haven't looked into it. It would be interesting to look into it. Yeah.
Okay. Thanks, Eric.
You can also write something on the chat so I can transfer it to Professor Scerri. Professor Aglos, please.
Thank you. Amazing talk. Thanks a lot. I have a comment on the left step periodic table. I think if we look alongside from the right-hand side of the table, it is as if we're staring at the structure of the atom going from the valence shell into the core electron. So basically, this is a very nice view of the whole thing.
Yeah. Thank you. What I also failed to say, and I think I'm saying the same thing as you differently, is that it obeys the n plus, or it reflects the n plus L rule more effectively than the traditional table, because notice every period is a value of n plus L. When n plus L equals 1, hydrogen, helium. When n plus L equals 2, lithium, beryllium, and so on. Each n plus L has its period. That's not the case with the traditional table. So maybe another sort of argument in favor of.
Right. Also commenting on the big ideas, I think a huge one is chemical bonding, because that came long before the quantum mechanical explanation of chemical bonding. So if this is not a seminal contribution of chemists, what else could be?
Exactly.
And then I also have a complaint as somebody that works with atoms and atomic spectroscopy. Everything we teach students, throughout the undergraduate curriculum, basically it's dominated by Hund's rule. So everybody understands the ground state of the atoms, and they behave as if there are not any excited states. So if you tell somebody that, for example, in nitrogen, the 3 electrons in the p subshell could go, 2 of them could go in one orbital, then this is not accepted because it's not Hund's rule, but this exists. So that's I just wanted to express that complaint.
Yeah. Okay. Yeah. Thank you.
Professor Kitsopoulos?
Yes, I would like to thank you for this wonderful talk. And I've been teaching freshman physics in the chemistry department for a while now, and I've rephrased it into atomic and molecular sociology. So I like the chemical philosophy aspect. But here's my question. Is math driving the world, or is the physics driving the world? I think the chemistry is a consequence. And so your approach was a top-down approach, and we do a bottom-up approach. Let's say the physical chemist. But these orbitals that are right there on this transparency, these are mathematical constructs. Do we really think nature needed basis sets to figure out what it's doing? And a lot of scanning electron microscopes, now they take pictures of molecular orbitals. And recently, a good friend of mine, Ben Whitaker, passed away in Leeds. And we had a lot of discussion on, these are just mathematical constructs because we know not better. And it's only a matter of time with artificial intelligence, quantum computers. A lot of these things will be obsolete. We'll just get the answer like we have now for all the protein structures. So I wanted your views on this and what you think about these, which are tied into what I'm seeing here.
Yeah. Let me select one of the things you mentioned, atomic orbitals. I agree with you completely. These are mathematical functions. They're not even real, right? They involve complex numbers, for one thing. Back in 1999, there was this dramatic claim, front page of Nature magazine, that orbitals, which up to now had been considered as constructs, had been actually observed for the first time. I was one of the people who immediately sent a paper. I published a paper in Journal of Chemical Education on this, arguing that this was nonsense, right? Atomic orbitals, molecular orbitals cannot be real. They're not real. As you say, they're mathematical constructs, extremely useful, but not real, certainly not picturable. Now, to your question about top-down, bottom-up, I'm not quite clear what you were getting at in the sort of hierarchy of chemistry, physics, mathematics. Do you want to?
Is the Pythagorean theorem there because physics requires it to be there, or is it because math requires right angles to be right angles? And I don't have the answer to that.
Yeah, nor do I.
Okay.
Nor do I.
Any other questions? So, Professor Scerri, what is your position on hunting new elements and trying to create and discover again new elements? Is there any purpose on that? Because a lot of, there's a lot of money going on at some groups in the world. I read a book, I think, when I was a student, The Periodic Kingdom from Atkins, that he was saying that we might find an island of stability somewhere afterwards. But what do you believe about that?
Well, apparently they found an island of slightly more stability, but it's not the dramatic stability that was being talked about for 20, 30 years. And yet, it's because it's not just the atomic number. You have to have the right number of neutrons as well in order to really achieve stability. And that's a sort of pipe dream. Students always ask, just yesterday, somebody asked me in a class, what's the point of, synthesizing these elements? Well, I like to say it's because it's a challenge. It's an academic, intellectual challenge to try and synthesize these elements and characterize them. There are all sorts of spin-off technologies, and it's a challenge to the mathematical theories that predict the properties of these highly unstable nuclei. And as far as I know, they are actively working on 119 and 120 as we speak.
Yeah, well, yeah, true. The thing that I'm saying to my students for the periodic table is that this is a universal truth. I mean, and this is the biggest contribution of chemistry. The things that you are seeing there, they're universally. It's a universal truth, but you can see it on your wall. I think at least this is good for the PR of chemistry.
Yeah.
Okay, if we don't have anything else, or would like to thank you one more time, especially for your midnight talk.
Thank you.
And thanks. Thanks, everyone.
All right. Nice to see you all.
Bye-bye.
Bye-bye.
Bye.
Good
Hope
night.
to come and visit sometime.
For
I
sure.
look forward.
Waiting for you.
Good.
Thank you.
I'm happy to hang around for a few more minutes if anyone else wants to ask, but
Yeah, I think, it was a very nice talk. So I think pretty much all the questions were covered.
okay. All right.
And
Okay.
I see on the chat a warm thank you for one of our students. So that's very good.
Yep.
Good. Yeah. Thank you, Leila. Bye-bye.
All right. Bye-bye. Thank you.